The most basic arithmetic operation is succession. Succession is just adding 1 to a number. The level above is addition. Addition is repeated succession. A plus b is equal to adding 1 to a, b times. Then we have multiplication. Multiplication is repeated addition. A times b is equal to adding a to itself, b times. The level above multiplication is exponentiation. Exponentiation is repeated multiplication. A to the power of b is equal to a multiplied by itself, b times. Now flip the direction. Instead of building numbers up, we can shrink them down. The opposite of exponentiation isn't just division, it's repeated division. And it takes us somewhere just as strange as titration did, except downward instead of upward. Take a number and divide it by itself repeatedly, or better, raise it to a negative power. A to the power of negative b is equal to 1 divided by a multiplied by itself, b times. This is where numbers stop being things we can picture and start becoming things we can only describe. For example, 3 to the power of negative 4 is 1 divided by 81, which is about 0.0123. That's still a number we can grasp. But push b further. 3 to the power of negative 27 is a number with a decimal point followed by more than a dozen zeros before a single non-zero digit appears. Shrinking a number this many times results in a fraction so tiny that it's hard for us even to picture it on a number line. But division doesn't always have to generate numbers this small. Once you divide any number by itself repeatedly, you often just approach 0, and 0 itself is trivial, it's the null point, the number that represents nothing at all. This is an easy example. But now consider an infinite tower of square roots of 1/2. We can write it as 1/2 titration downward to infinity, or, more precisely, using a limit as x approaches infinity of 1/2 raised to the power of 1/2 to the x. Surprisingly, this infinite tower of shrinking roots doesn't collapse to 0. It converges to a fixed, non-zero value, because every square root pulls the number back up toward 1 even as the exponent pushes it down. Smallness, it turns out, has its own strange stability, a floor beneath which some processes simply refuse to fall. So far we've been using ordinary exponents. Unfortunately, there is no standard notation for a reciprocal tower the way there is for titration, but we can describe it using nested fractions. 1/a, all raised to the power of 1/a, repeated b times, lets us define an operation just as extreme in the small direction as titration is in the large direction. Call it micration repeated reciprocal exponentiation. Micrating 3 down 4 levels means take 1/3, raise it to the power of 1/3, then raise that result to the power of 1/3 again, and again. Each layer doesn't just shrink the number, it shrinks the rate at which it shrinks. 4 layers down, you land on a number so close to 0 that writing out its decimal form would take more digits than most calculators can display. This number is unimaginably minuscule. But we don't need invented operations to find smallness that breaks our intuition. The real world is already full of it. Consider probability. The odds of shuffling a standard deck of cards into one specific, exact order are 1 divided by 52 factorial. That denominator is a number with 68 digits. The chance of it happening is so small that if every person on Earth shuffled a new deck every second since the beginning of the universe, the odds of ever seeing that one exact order are still, for all practical purposes, 0. Now, go smaller. Consider physics. The Planck length is roughly 1.6 times 10 to the power of negative 35 meters. That's a decimal point followed by 34 zeros before the first non-zero digit. It's considered the smallest meaningful unit of distance in our universe shrink further, and space itself may stop being a coherent idea. A single proton is about 100 million times larger than the Planck length. Just imagine how small this distance actually is. Go smaller still. The theoretical lower bound for the mass of a neutrino sits near 10 to the power of negative 37 kilograms. Numbers like this stop being measurements you can visualize and start being placeholder symbols standing in for a scale of reality no image or metaphor can represent. But even these tiny real-world numbers are enormous compared to what pure mathematics can produce. Remember Graham's number, the almost incomprehensibly large integer built by stacking arrow operations 64 layers deep? Now take its reciprocal, 1 divided by Graham's number. This is not just a small number. It is a number so close to 0 that, if placed anywhere near 0 on a number line the size of the observable universe, no measuring device ever built or theorized could distinguish it from 0 itself. And yet, mathematically, it is not 0. It is a precise, defined, non-zero quantity. Now recall tree of 3, the number generated by the tree seed game, so large that Graham's number is embarrassingly small by comparison. Take its reciprocal too, 1 divided by tree of 3. This number is so small that even the difference between it and 0 cannot be expressed in any physically meaningful unit, not atoms, not Planck lengths, not any measure our universe provides. It exists purely as an idea, a number defined by logic rather than by anything we could ever locate on a physical scale. We can keep going. Just imagine how small 1 divided by 3 pentated to 3 would be, or 1 divided by tree of 3, or the reciprocal of a number already too small to picture, shrunk again. Just as there was no largest number when we kept stacking arrows upward, there is no smallest number when we keep stacking reciprocals downward. For every impossibly tiny fraction we can name, a smaller one is always waiting, defined just as precisely, just as validly, sitting quietly between that number and 0. These numbers are beyond our comprehension in terms of size, not because they are large, but because they are small in a way nothing in our physical experience prepares us for. 0 feels like an ending, but mathematics keeps building rooms between any number and 0, rooms smaller than the last, forever.